SwayamPrabha. Digital India. Educated India.
Hello everybody and welcome back to this series of lecture on elements of solar energy conversion. Today we are here at lecture number 27. Okay. So, we were looking at the compound parabolic collector or CPC, and in the last class we have derived the expression for the reflector area. So, reflector area, which is also called concentrator area, because concentration is happening here through reflection. So, this expression we ended up with, and this simple expression is valid only for small concentration ratio which is less than 3. Typically, these compound parabolic collectors are used where the requirement of concentration ratio is not that high, but the requirement that you do not need to use a tracker, that is even more important, and that is why for small concentration ratios we use this CPC, and the concentrator area or reflector area is expressed like this. Now, another important thing, quantity to know for CPC is the average number of reflection. Okay. So, if you look at the CPC geometry, okay, some ray may go multiple number of reflection before they reach the receiver surface, or some ray may directly come to the receiver surface. So, all the rays are not going through equal number of reflections. Okay. So, here reflections. So, what is that equal, what is the average number of reflection? That is important, because that will tell us what would be the intensity due to these multiple reflections, because every time, if suppose the reflectivity is 0.9. So, 90% of the ray will be reflected and the 10% will be lost or absorbed or something. Okay. So, this 90%, now if you have 2 reflections, then 0.9 into 0.9, that will be the effective fraction that will be available to the receiver. Now, if you have 3 reflections, then it will be 0.9 to the power 3. That is how the average or the number of reflection will change the intensity for that particular ray. Now, it can be shown that this average number of reflection is dependent on again the acceptance half angle, which is the quantity related to its geometry, and that is the thing that always or all the important parameters related to CPC are dependent on this acceptance half angle. Okay. So, here this area of reflector A con and divided by the aperture width and the length of the collector minus 1 minus sin theta A multiplied by 1 plus 2 sin theta a divided by 2 sin square theta a. In case you are interested in the derivation of these expressions, you have to go to the original sources, the papers, the research paper where these have been derived, and you will find the relevant reference from the textbook, which is by Sukhatme and Nayak. Okay, we are not going through the derivation here, we are just mentioning the formula so that you can design or you can find the relevant quantities related to the design. Okay. Now, so this is concentrator, and this average number of reflectivity or the effective reflectivity of the collector will be the reflectivity of the surface to the power this average number of reflection. Okay. So, this is an important quantity that you will require. Now, we have looked at the optical part of it, what would be the area, what would be the geometry, how it can accommodate larger or inclined incidence on the aperture plane. So, now what we are going to do is we will look at the performance analysis of a CPC. Okay. So, in this figure you can see that we now have the CPC, and at the bottom at the receiver part we have this heat collecting arrangement. So, at the bottom of the receiver we have this heat collection arrangement. Typically, as we have seen for flat plate collector, we have the tubes that are running below the absorber plate, and we have this insulation, okay, and the whole thing is put in a box. So, that is how the heat is collected from the CPC. Okay. So, first let us put some symbol for all the relevant quantities. So, W you have already looked at, it is the aperture width, L is the length perpendicular to the plane, or you can say length along the fluid flow direction, right, and 2 theta a is our acceptance angle, okay. B is the absorber or receiver width, okay. So, let us say that N is the number of tubes which are collecting the fluid, collecting the heat from the receiver plate, okay. And we can assume that the aperture is oriented towards south direction, south for northern hemisphere again, and it would be north for southern hemisphere. So, basically towards the equator, okay. And the beam direction is within the acceptance angle for the CPC, okay. Then only it will reach the receiver portion. Okay. So, if this is the case, then what we can write, the beam radiation flux falling on the aperture plane is IB into RB, right. IB is the beam radiation intensity on a horizontal plane and RB is the conversion factor which takes the tilt into account. Okay, this you have seen earlier, so you know how it comes. And the diffuse part, as the concentration ratio for CPC is not that big, usually it is within 5 or maximum 10. So, the diffuse radiation concentration will also be important for this low concentration ratio CPC. Okay. For higher concentration ratios such as parabolic trough or parabolic dish, as we see will see next, there the beam intensity is so intense that you do not need to include diffuse radiation, it does not make any significant difference. But here we include diffuse radiation because beam intensity is not that big. So, the diffuse radiation flux within the acceptance angle is your ID divided by C. Why we call it divided by C? Because the diffuse radiation is coming from all kinds of direction, right, and only a fraction of that which is coming inside the aperture is being coming on the receiver plane. So, we have to divide it by concentration ratio C. Okay. So, again it involves, this particular expression involves a long derivation which we are not being able to cover here. You can look that up from the original papers. Okay. So, the total intensity is our IBRB plus ID divided by C, right. Now, when we know the intensity, we now know what is the absorbed radiation, what is the per unit area, what is the absorption. Okay. So, that is the total intensity multiplied by the transmissivity of the cover. So, we are assuming that we have a transparent cover at the aperture. Okay. So, that transmissivity will come into picture and then you will have this effective reflectivity, whatever intensity is coming in the aperture, okay, whatever is coming, they will be reflected and the effective reflectivity rho effective will be multiplied for the absorbed radiation part, and then the other factor is alpha. Alpha is the absorptivity of the receiver. So, here let me write this tau is transmissivity of the cover, okay. Rho is the effective reflectivity, as we have seen few minutes ago. Okay. And alpha is the absorptivity of the receiver plane. Okay. So, here you see that instead of flat plate collector, the expression of S has changed little bit and we have to incorporate that in our analysis. Now, what we can do, this dQu, the useful heat gain rate, that you can say okay, here one thing I missed, that here this S is per unit aperture width, because the intensity everything we have talked about, it is on the aperture. Okay. So, the S will also be, it is normalized per unit aperture width, not per unit receiver width. So, that you have to pay attention to. Okay. Now, this dq, if we say that useful heat gain rate, okay, and how will you get it? By energy balance for an elementary slice dx of the absorber plate at a distance x from the inlet. Okay. So, then as you have seen earlier, it will be S minus UL by C. Okay. For concentrating collector, you have this UL by C factor, which is unlike the flat plate collector. Okay. And this is multiplied by aperture width W into dx, because this S is per aperture width. So, everything we have taken, even the UL, which is the effective loss coefficient, that also we are taking in terms of absorber width or absorber plane. Okay. So, similarly, I mean we are skipping all the steps, we can just say that similar procedure for flat plate collector, or what we have seen the parabolic trough collector earlier, what we will get, this QU will be FRWL multiplied by S minus UL by C, then TFI minus TA. This you can write when you have this collector heat removal factor involved. You can write in terms of the fluid inlet velocity temperature and the ambient temperature, isn't it? This you have seen earlier. Only thing you need to pay attention is here. So, here you are using the aperture width, not the receiver width. Okay. And here we introduce the concentration ratio. Okay. So, these two you need to pay attention to, which is unlike the previous cases. Okay. So, here in that expression, Fr is nothing but mass flow rate into specific heat divided by BUL multiplied by L. Okay. So, B here is the receiver width. Okay. Now, in the heat removal factor, the receiver width is coming into picture. Okay. Here in the heat removal factor, the receiver width B is coming into picture, but in the expression of QU, the useful heat gain rate, we have W, which is the aperture width. Okay. So, the rest of the expression is very similar, minus F prime B UL L divided by m dot Cp. Okay. So, F prime is what? It is collector efficiency factor, right, and that F prime. So, here I should write where and here again where. So, this collector efficiency factor can be expressed as 1 over f prime is equal to u l multiplied by 1 over u l plus b divided by n pi d I h f. Okay. So, this you can see that this is for the heat loss part, heat loss to ambient, that is how this u l is related to, and this part is heat transferred to the working fluid. So, the working fluid details came into picture. N is the number of tubes, pi d I is the in the pipe what is the inlet perimeter, and h f is the heat transfer coefficient inside the fluid. Okay. And B is of course the width of the receiver. So, that is how we can get the heat transfer to the fluid from the compound parabolic collector. Okay. So, so far we have looked at the two dimensional parabolic collectors. One is PTC, which is the parabolic trough collector, and the next one we have looked at is compound parabolic collector, which is nothing but the combination of two consecutive parabola, and they are put in a certain algorithm, according to certain algorithm, and that is how we receive less tracking requirement produces significant amount of concentration. Now, next what we are going to look at the higher concentration ratio if we target, then we have to go for 3 dimensional or 3D concentrator. So, higher concentration ratios are obtained by using 3D concentrators, or what we often call point concentrator. Instead of a line, we now concentrate in a point. So, that is how we increase the concentration ratio. So, first thing here, the most common is called the paraboloid dish collector. Okay, where its surface of revolution we are using, and the line that we are revolving, that is a parabola. Line is a parabola, or rather part of a parabola, and we are revolving that around an axis, and that is how we get the paraboloid shape, and paraboloid dish collector is giving you a point concentrator. So, the image that you are seeing, this is for an actual paraboloid dish collector, which is named Euro dish. Okay. So, this was the a major event happened in Europe around 2010, where few countries came together and designed this particular solar collector, where you can see that this is a large paraboloid dish, and where you are concentrating? You are concentrating at a small area. I mean, in principle you are concentrating at a point, but of course, in practical you have practical limitation that you have to have a significant amount of area. So, you can say that this is where the point concentration is happening. Okay. So, the rays that are falling on the aperture are getting reflected and reaching that point concentration where we have some, either the heat is being collected by some fluid or that heat is being used in some engine itself. So, in case of this Euro dish, what we have, the glass mirrors of reflectivity, high reflectivity 0.94, okay, and we have that the diameter is 8.5 meter. Okay. So, you can imagine that it is a big paraboloid and total glass area is 60 meter square. Okay. And we have a cavity type receiver here. What we mean by that we will see in few minutes, with an aperture diameter of 15 centimeter. Okay. So, you can see the large area 60 meter square is the mirror area or the aperture area, that part is getting concentrated into a small area of 15 centimeter diameter. Okay. So, you can imagine the concentration ratio there, you can calculate as well. Okay. And here the focal length is 4.5 meter. Okay. Now, this receiver here, some fluid is not flowing to take that heat away. So, the receiver is directly attached to the cylinder of a Stirling engine. Stirling engine is the typical solar engine which runs on external heat. So, any temperature difference it can convert into power, and please look that up how a Stirling engine works, but for this paraboloid dish it is often used along with some Stirling engine, and this particular Euro dish one gives you the peak output of 8.5 kilowatt. Okay. So, this 8.5 kilowatt of energy you can get almost free. So, installation cost is of course there, but there is no fuel cost, right. So, that is why these solar paraboloid dish they are very popular. And we also have one very good example in our country, in India. So, the figure that you see here is at Mahanand Dairy in Latur, Maharashtra. Okay. So, this is a dairy farm and they have installed this particular paraboloid dish, and they are not producing power with it, but what they are doing? They are producing process heat in the form of pressurized steam. Okay. So, for milk industry or dairy industry, what you need to have process at certain pressure, process heat at certain pressure and temperature for the milk processing. Okay. So, for pasteurization you need to have the heating at certain pressure, you cannot go below that pressure because then the pasteurization process does not happen. Okay, so in this case what they are having is 20 bar pressure, okay, and temperature of about 180 degree centigrade. Okay. So, that kind of heat it is generating, and per day it can deliver 1.6 into 10 to the power 6 kilojoule of heat. Okay. That is a large amount of heat that it can produce, again just free. Okay. It is just converting solar energy into this, and what can it do? It can do 20,000 to 25,000 liters of milk per day get pasteurized. Okay. So, that is very practical example that we have. There are, so this is also quite old, but there are new paraboloid dish collectors which are coming up for many agricultural industry, other industries where chemical or even dyeing industry, textile industry, where process heat is a big part. And usually earlier we used to burn fossil fuel, gas or coal, but for this green push now what we are trying to do, we are using the solar dish, and we can get it almost free. Okay. So, now the next concept we are going to discuss is called central receiver tower. Okay. Again it is a point collector, and what it does, in a big field you just put in the middle of that field you put a tower, okay, tall tower, and on top of that you have some collector, okay, and around it in circular positions you put lot of these reflecting surfaces. Okay. These are reflecting surfaces. So, here you see these are called heliostat. Heliostat means what? Helio means sun and stat means static. So, basically with respect to sun it does not move, it is static. So, what it means is that it perfectly tracks the sun, so that with respect to sun that position of the reflector is static. So, what it does, from whichever direction the sun rays are coming, the reflectors they are individually tracked. So, they ensure that whatever ray is falling on it, it is reflected back to a central point. Okay. That is how this central receiver tower works, and all of these are doing the same thing. Okay. They are reflecting the sun rays to a central point, and you have to put this central receiver at some height, then only all these receivers will be able to work without interfering each other, without shading or blocking each other, right. So, that is how a central receiver tower works. So, basically this means that these heliostats are reflecting surfaces which track the sun, so that all the reflected rays are directed to the receiver. Okay. Now, you can see an actual figure for this central receiver tower. Okay. So, again this is actual figure, and you can see here that the central tower is here, okay, and receiver is at the top of it, and all these reflecting surface individually you can see all these reflecting surfaces, and there are lot of them, okay, and all of them are oriented in such a way that their reflected ray reaches this point. That is how you can generate a huge amount of concentration ratio. So, the concentration ratio can go as high as 2000 or 3000. Okay. It depends on the design, and the concentration ratio can go really high, but if you go that kind of high concentration ratio, the temperature that you can reach can also exceed 1000 degree centigrade. So, when you increase the temperature, you know the Carnot efficiency increases and the efficiency of the power plant increases, because temperature signifies the quality of heat. When the temperature is higher, that heat is more useful, the quality of heat is more. So, in a heat engine it will produce more power. Okay. So, that is why for high temperature, even supercritical power cycles, we cannot use the parabolic trough or these things, but we can use this central receiver tower where the temperature can go really high. Okay. Now, another variation you can have with these things with multiple towers, with multiple receivers. So, multiple tower CRT system. Okay. So, that is also possible. Why do we need it? We do not have enough time to go in details of designing this central receiver tower or heliostat field layout. There is a complete theory of that, but what we can say that when the, like for the last figure you can see heliostat towards the edges. So, heliostats towards the edges are less effective, because of cosine loss. So, when the receivers are or the heliostats are forced to make the angle change a lot by reflection. So, the angle between the incoming ray and the reflected ray tells us that what would be the cosine loss. Okay, the minimum the angle. So, in the previous figure you can see here that this angle is more for the heliostat which are towards edge, okay, which are near the central tower, this angle is smaller, okay, and this particular angle, this angle actually dictates the cosine loss. So, when that angle is larger, you will have less amount of contribution from the heliostat towards the edges. So, that is why we cannot go for very large field, then the effective contribution of the edges will be low. So, in that case what we do, we divide the field with more number of receivers. So, for very large field, cosine loss is unacceptably high, and hence we divide the field with multiple receivers. Okay. So, this is why this multiple tower CRT system is used. Okay. So, that is a a variation of the central receiver tower system, and if we look at a particular heliostat, then what you will find that a large reflecting surface, which is this. So, large surface with lot of mirrors placed on it. So, yeah, so these mirror modules, they are placed on them, and you have a support pedestal here, and this whole thing is connected to some drive mechanism. Okay. So, this drive mechanism, what it does? It allows the two axis tracking of the sun. Okay. It is, of course, it is automated, depending on the location of the sun, it orients itself so that it reflects properly to the receiver tower. Okay. That is how a heliostat would look like, and in the receiver part what we have is the tower, and on top of that we have the receiver. So, there can be two, so these are receivers, and there can be two different kinds of receiver. One is called external type and other one is called cavity type. Okay. So, external ones, how do they work? Usually they are of this cylindrical shape. Okay. And the outside is the absorbing material, you have some coating which can absorb all the radiation it gets, and at the back side you will have arrays of these tubes which are taking the working fluid. So, at the back of the absorber surface we have arrays of tubes that carry the working fluid. Okay. And in case of cavity type, what you have? You have not the external surface, but you allow the concentration happening inside a cavity. So, a small cavity is there through which all the rays go inside, and there you have this array of tubes carrying the working fluid. Okay. And another kind we can have, which are now getting developed, which are called volumetric receivers. Okay. Other than the external or cavity type, we have these volumetric receivers, where we have this highly porous materials like metallic wire mesh, okay, or ceramics or honeycomb structure. These are all for the purpose of increasing the area of heat transfer. So, area of heat transfer is large. Okay. And air or some gas is used, often helium is used for its desirable properties, is used as the heat transfer fluid. Okay. So, these are different kinds of receivers, the heliostat field geometries. Now, if we want to quickly analyze it, let us assume, so let us do quickly this CRT analysis. Okay. So, let us assume that we have n mirrors, each having area AM. M stands for mirror and A stands for area. Okay. And it covers, or rather they cover, an area AG on the ground. So, you can see that the heliostats cannot be placed continuously. You have to put gaps in between, because otherwise the incoming rays will be blocked by a neighboring heliostat, or the outgoing ray or the reflected ray will be blocked by the neighboring heliostat. So, we have to keep these gaps between the heliostats, and that is why the area, the whole heliostat field area, only a fraction of that is getting used as the reflector area. Okay. So, the fraction of ground covered by the mirrors is psi. Okay. That we can say, because it psi is always less than 1, and it is usually much less than 1. Usually psi is around 0.4. Okay. Only 40% of the ground is covered by the mirror area. So, now what we can write, A n into AM will be psi into AG, right. So, mirror area, only psi fraction of it will cover the ground. Okay. Now, if we have this tower height as in this figure to be h, okay, and the area of receiver is AP, then what we can write, this QU will be IB multiplied by, this is a new thing which I will explain in a bit, multiplied by rho tau alpha AM minus UL AP TPM minus TA. So, rest of the thing is very familiar, only thing we do not know is this part, right. So, why that is coming? Because now you will see that each ray is falling on the receiver surface at a different incidence angle. So, earlier we have seen for the plates and other receivers we have a constant receiving angle, right. So, or the incidence angle, but here you can see all these different reflectors, they are putting the rays back into the receiver, and the incidence angle is continuously changing for each of the heliostat contributions. So, that is why we cannot take a single RB. So, a single RB is ineffective, what we need to have? An average RB. Okay. And how we can find that average RB is nothing but 1 over n the total RB of all the different heliostat contributions. Okay. So, that is the major thing. So, what you can write now, this QU you can write IB multiplied by RB average, and then the mirror area NAM is nothing but psi AG, right. So, this is equal to NAM, total mirror area, and then this thing will be multiplied by the reflectivity of the mirror surface, tau, that means transmissivity of the cover surface, and alpha is the absorptivity of the receiver surface, okay, minus the loss term which is happening with ULAP multiplied by TPM, which is the mean plate temperature, and TA, the ambient temperature. So, that is how this heat balance is done. Okay. And here I should mention the concentration ratio C is nothing but your total mirror area, that is the area, effective area of aperture divided by the receiver area, or you can write psi AG divided by AP, right. Now, we can have this kind of receiver where you have a conical receiver surface, okay, which will basically reduce the effect of tilted incidence. This will reduce the effect of tilted incidence. Okay. So, that is often used. Now, we are not going to detail how those receivers are designed and all, okay. That should be part of your further reading, not in the part of the course. So, here up to this course, today we are at 27th lecture. Up to this, what we have completed is all the background that we require for solar energy conversion, and all different kinds of, or rather major kinds of, the thermal solar energy converters in terms of flat plate collector or the concentrating thermal collectors, okay, including the central receiver tower, which are used for large scale solar thermal power plants. Okay. Now, from the next class onward, for the rest of the lectures, what we are going to do is the photovoltaic part, which you often see, which is the most commonly observable solar energy conversion device, the photovoltaic panels. How do they work? We will look at the basics of them in the from the next class. Thank you so much.